So, today we're going to be talking about convergence tests. All right? And the convergence tests, the most important thing is to have a way of knowing which test to use when. And for this, I've set up a flowchart. The flowchart starts always with the divergence test, also known as the nth term tests. You're looking to see if a sum converges, if you add up the numbers and they come down to some limit of some actual number. That can't happen if you're adding an infinite number of things that just never go to zero. And so the first test you always use is the divergence test, the nth term test. Check that nth term and see if that goes to zero. If it doesn't, you are done. This thing diverges. Otherwise, okay, if it does go to zero, then the next thing you want to check is to see if it's alternating. If it's alternating, it converges. Yay, you're done. Almost. But there's the thing. You check to see if the nth term goes to zero. First thing. If it does go to zero, then you got more work. And the next thing is just to check to see if the sign is changing in each term. You got a -1 to the n term somewhere in a sub n. If it's alternating, it's changing sign, yay, it converges. You're done. Almost. Otherwise, you're going to have to bring in other tests. Now, if it converges, though, you have to go a little bit further than that. We're going to ask if it's converging absolutely. And what that means, does it converge if you get rid of the sign changes? Or does it converge if you're looking at the sum of the absolute values? That's where the term absolute convergence comes from. And yeah, I can see that one student already had been popped out, and this is one of the reasons why I'm recording this for later. Also the reason why I'm temporizing right now, because I can see that the student is trying to reconnect right now, and I'm hopefully get her back in before I continue. I'm seeing reconnecting. I'm not going to be able to do this for everyone, but because it's a small class, I'm going to see if I can't do that. And it looks like this is taking more than just a few seconds. So I'm going to continue. And I'm sorry, wait, God, please, let's give it a couple more seconds. A couple more seconds. I really want to see her. And she's back. No, she's not. She's gone. I think she's probably relaunching. Again, guys, if things going too bad with the browser, I hope you all have the Blackboard app on your phone, and that's always your backup, because that's pretty stable now. And it's not that bad. It's kind of difficult to have a phone and take notes, because I know you all going to want to take notes, but there it is. But this slide right there is one of those perfect things that you're going to want to work with. Now, if it passes the divergence test, the nth term tests, and it's not alternating, now do other things. The other 10 things we're going to do, I'm going to look at 4 specific tests beyond this, okay? And the first one, it's all going to depend upon what you're looking at. If you look like something that looks like a rational function, something that's similar to, polynomial divided by polynomial, okay? Or powers over powers. What you're going to want to do is try to look at it and see if it's something that looks like you can reduce it or compare it to 1 over n to the p power. And if that's the case, you can use a p-test. And then, if, according to the p-test that we've looked at before, if that power in the denominator is less than or equal to 1, it'll converge. It'll diverge, right? And if the power in the denominator is bigger than 1, then it's going to converge. If it's equal to 1, that's the harmonic series. 1 over 1 plus 1 over 2 to the first plus 1 over 3 to the first. That's the harmonic series. And we know that one. She's back. There we go. Yeah. And I wanted to mention to you guys, as I said, that I know you guys are probably going to miss a few things. Some of you guys are going to miss a few things. That's why I have this being recorded. Deborah, I think I lost you just as I went from alternating and going to 0 on the nth term means it's converging. The only thing that's different after that, if it's converging, you also have to check to see if it converges absolutely. And for that, just take the absolute value, get rid of the sign changes, and check to see if that still converges. And if that does still converges, then you can say that it converges absolutely. That's for the languages. Beyond that, we have 4 tests we're going to check. The first is the p-test. That's when you're looking at rational functions or something that looks like a rational function. Or you can also do it with other powers that aren't integer, but that's mostly what you're looking at is just rational functions. And then, if the power in the denominator is bigger than 1, it will converge. If it's less than 1, it will diverge. And if it's equal to 1, you're looking at something comparable to the harmonic series, which diverges. The next thing we do, and this is the most important test, guys, this is the ratio test. This is the one we're going to be using with power series, okay? So that's the really important one. The ratio test is the most important of any of these. So that's the one you can probably guess that I'm going to make sure that you guys are square on. Now, for this one, we're going to construct the ratio. And the ratio means the next term divided by this term, okay? A sub n plus 1 divided by a sub n. What we're doing is we're mimicking it as if it was a geometric series. And for the geometric series, if the ratio is less than 1, it converges. And we actually did some calculations on that and did some things where we calculated geometric series, right? And that's why, just so we could be ready for the ratio test and taking ratios. Now, ratio tests, if the ratio is bigger than 1, then it's just going to blow up. Each term gets bigger and bigger and bigger and bigger. It's exponential growth. And that blows up and it will never converge. If it's less than 1, that's all you need. It's a exponential decay, and we know that we can integrate that. That's an improper integral that we've looked at before. And if it doesn't do it, if it's in between, then the test fails. And this is going to be true for both the ratio and the root test. Okay? Whereas with the p-test, you actually get a result. If it's equal to 1, you know it also diverges. So that's the difference between the p-test and the ratio and root tests. With the p-test, you don't get a fail criteria. But on the other hand, you can't always use the p-test because it doesn't always look like a rational function. But for the ratio test, you actually have greater than 1, less than 1, and test fails condition. Now, you're going to use this test anytime you see a factorial. That's kind of what it comes down to on the ratio test. If you see a factorial in the expression, if a sub n looks like something with a factorial term in it, generally in the denominator, that's where you'll see it, then you're going to want to use the ratio test because the factorials are just built. Anything with a factorial is just built for using the ratio test. Now, sometimes you're going to see as well the terms themselves look like something taken to the power n. Okay? Everything goes up to the power n. And that's when you use the root test. Like the ratio test, you're going to test the inner thing, but not the ratio this time, just the thing that's being taken to the power. You're going to test the root. If the function looks like it's being taken to the nth power, you get rid of the nth power and you look at what's inside. And if what's inside goes as a limit that's bigger than 1, it'll diverge. If what's inside is less than 1, it will converge. And if it's equal to 1, again, the test fails. Now, if none of these have worked, we got the nth term was going to 0, so we know that we're valid at least. It's not just going to immediately diverge. It's not alternating. It doesn't look like a rational function I can use the p-test on. I don't see any clean way of getting a ratio test, or the ratio test fails. I can't get a clean, it doesn't look like something taken the nth power, or the root test fails. All we're kind of left with is, can we integrate it? I mean, there are other tests that we could use, but these are the only ones we're going to cover. And if you can integrate it, it's going to be an improper integral, right? And if the improper integral diverges, the sum diverges as well. And if the improper integral converges, then it's integrable. So that's the whole story on those. Okay? That's the overview, and this is the flow chart you're going to want to study and memorize. Because, yeah, it's not that tough, right? Run through it a couple times. Now, let's start looking at the individual tests. And the first thing I want to look at is the divergence test. That's also known as the nth term test, because you look at the nth term. And the answer is fairly simple. The series, based on the sequence a sub n, diverges if the nth term doesn't go to 0. All right? And that leads us into the next real fast thing, and that is checking after you've checked the divergence test. If it's alternating, it converges. And that's all you have to worry about. It doesn't have to alternate all the time. It has to eventually be alternating. In the same sense, the nth term doesn't have to, you don't have to go to 0 immediately. You can do weird things. It doesn't have to be monotonic or any of that. As long as it becomes monotonically and monotonically approaches 0, you're okay. All right. Now, if the alternating test works, okay, and you know that it converges, we'll often ask, what about absolutely? Because sometimes you get series that they'll converge on one side of the axis and they'll diverge on the other side. So I have students kind of dropping in and out here, and I'm just going to have to keep on going. And in that case, we're going to test everything else just with the absolute value. And if it converges when you get rid of the sign changes, when you look at the absolute values, then we say it converges absolutely. That's what the language is from. Now you see there's a note at the bottom, right? All these tests are going to be done with the comparison test. Okay? So you don't actually have to have it as something that looks exactly like a p-series. If you can compare it to a p-series, it doesn't have to look like a geometric series. You can compare it to a geometric series. It doesn't actually have to be something you can integrate. If you can compare it to something you can integrate using the regular comparison test. You want to be smaller than something that converges to say that it converges, and you want to be greater than something that diverges if you want to say that it diverges. Okay? So, let's go ahead and just start up some examples in here. Keep an eye on the time. We're doing okay. I think we're doing very good. I think we're doing very good. Okay, so let's look at an example on a p-test. Okay. Let's check the sum. Okay. (3n) plus 7 over 5n minus 2. Okay? I haven't got to a p-test yet. We're just looking at this right here. Now, let's look at this. This, of course, is always going from n equals 1 to infinity. All right. So what's the first thing we do on these guys? What's the first thing you always do anytime you're confronted, when you're seeing a series in front of you? What's the first test you always check? Put it in the chat. What's the first test we always check? The first test you always, what's the first test always, always, always? Let me unzoom a little bit. What's the first test we always use? If it goes to 0, that's right. That's called the Nth Term Test. It's called the Nth Term Test. It's also known as the Divergence Test. I like to think of it as the Nth Term Test because that tells me what I'm looking for. On this one, I'm going to check now. The limit as n goes to infinity of 3n plus 7 over 5n minus 2. Okay? I think you can eyeball. What's the limit on this? What's the limit on this? Anybody? Yeah, that's right. That's right. It's going to be 3/5, right? I mean, we could get really fancy and use L'Hopital's rule on this. But the general rule is if you're looking at as it goes, it is something improper, is it going to infinity? The basic rule is just really, really simple right there. Just eliminate all minor terms. If I eliminate the minor terms, if I eliminate the minor terms, I'm looking at this. 3n over 5n. Minor terms being powers less than. And so that right there is pretty obviously 3/5, right? Because you can just cross that out. Okay. So that one right there, we can say immediately this one diverges. Okay. Now, let's try a second example now. Okay. Where's my examples? Almost out of coffee too. So here we go. Okay. So let's check this one, guys. Let's check this one. What's the first test we always try? Anyone? I suggest call it nth term. Nth term. Yeah, that's the best idea, Patrick. Yeah, call it nth term. If I try the nth term test, what is it? What do you see if I try the nth term test? Two sevenths. Yeah, pretty obvious. The limit infinity, a sub n, is 2/7. And this means we diverge. Okay. Now, the next thing I want to look at here we go. And everybody says, oh, alternating. Yay, alternating. Okay, so what do we do with this one, guys? What's the first thing we do with this one? Okay, anybody? What's the first thing we do with this one? See, I can wait. I can wait. What's the first thing we do with this one, guys? Nth term test. That's right, Kayleen. Don't get distracted because you, oh my God, I'm seeing it's alternating. Yay, 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 yay. The nth term says diverging. Okay. Now, let's get a real example in there, aside from your homework. All right. So here now we've got a last example, right? And my question is, what happens with this one, guys? Anybody? Anybody? Yeah, we do the nth term test first. We'll do the nth term test first. And does the nth term go to 0? Does the nth term go to 0 on this? I'm gonna run out of space here, but that's okay. This is the last one. What will be the nth term? Nth term looks like to me -1 to the n over n squared. And why do I say that? Okay. Sine n doesn't do anything nice. This is sine of 1, sine of 2, sine of 3, not degrees, mind you, but radians. And this could be all over the map as it runs through there. It never repeats. It will never repeat. Yeah. It's like Kayleen's having some issues with the session today. It never repeats, but the sign always stays less than 1. Anytime we see sine or cosine, I always think of just replacing it with number 1 and considering it absolute value. Yeah? So this is going to be comparable, even though sine is going to go positive and negative, so it's not always going to alternate, right? I can compare it to -1 to the n times 1 with n squared plus 3n plus 2. And as such, I'm saying, oh, look, it's the nth term does go to 0, right? I'm looking like 1 over n squared. That's going to go to 0, right? And in addition, I'll be able to go ahead and say now that it's also alternating. Anytime the nth term goes to 0 and it's alternating, I can work with this. Similarly, I could have done this the same way. With n minus 5, because then it would look like and this, again, would be something I can see is going to converge, even though it would not absolutely converge. Because if I get rid of the sign change, this looks like an alternating series. Yeah? It would be difficult to show, yeah, but it looks like an alternating series if I get rid of the sign change. But with the sign changing, so long as it's alternating, sines and cosines you replace with 1, yeah. Sines and cosines of anything, you just replace them with 1 for your comparison. That's your first thought. Yeah. Okay. But those right there, you can do those in the homework, and it's fairly straightforward. And those are kind of nice. All right. Now, let's talk about p-tests. And p-tests come from rationals. So p-tests come from rationals. Anytime you look like something looks like a rational function. An example here. Yeah. Well, let's go ahead and just continue this. And the basic idea behind the p-test is you're looking at a rational function generally. And you want to bring it down to something over n to the p, okay? Give an example here so you can see it. Here we go. There we go. And again, all these were from 1 to infinity, and I'm not going to write that every time because it should be understood that we're always looking at these infinite series. All right. Let me get myself squared away there. There we go. Okay. Now, take a look at this one, guys. Yeah. Let me kind of get myself squared away so you can see it better. Hopefully that's better, right? Okay. Now, look at this power, this thing that you're seeing at right here, okay? Right? What does the top look like to you? What does the top look like it's comparable to you? Does that look like a power of n? What does it look like? Top looks like what power of n? That's right. It looks like the cube root of n. The plus 2 doesn't do anything. It just doesn't. It's just, as n goes to infinity, it might as well just be n. And you can reach on into the cube and get rid of those. So it looks like n to the 1/3, right? And the bottom looks like what? Looks like n squared, yeah? And we know things about this, right? What's 2 minus a third? That's 6 minus 1/3, 5/3, right? 2 minus 1/3 is 5/3. So I'm looking at 1 over n to the 5/3. Yeah, that's what I'm seeing here. And then once I've simplified it, now it looks like a p. Now it looks like a p series, and it's going to be comparable to the p series. Okay. By putting in a scalar or something like that, you can always turn these things so it's bigger than or smaller than. So you can always work with these. If you can do one of these simple transformations, you can use it. You know, you don't have to necessarily worry a whole lot about whether you're going to be able to do the comparison with this. Yeah. If you could just get rid of minor terms and get back to this, the p-test is going to be valid. Okay? So, and the idea behind this is the same thing. In a sense, we're kind of like falling back on the integral test, because the integral test says I can integrate 1 over x to the 5/3, right? That's x to the negative 5/3, and I take it up, it's x to the negative 2/3 over negative 2/3, and integrate that from 1 to infinity. Turn that around, and it's x to the 2/3. Yeah. And the number, it just pops out. And you can see the actual number comes out on the definite integral, the improper definite integral. And that's going to be enough. That's going to be enough. So this one's going to converge. Now the idea behind this one, because you'll see everything else, you're going to be looking like less than 1 is good, greater than 1 is bad. This one turns it around, but the reason it turns it around is the thing that you're comparing, the one that you're looking for, is in the denominator. That's why. Unlike the ratio and the root tests, greater than 1 is good and less than 1 is bad. Okay. The other two tests, the next two tests we're going to look at today, are always going to be the form greater than 1 is good, less than 1 is good, and greater than 1 is bad. But this one turns it around. And again, this test fails if p is equal to 1. Okay. And if p was equal to 1 and it was still going to 0, because we always, when you're in any of these situations, that you've checked the nth term test, right? So you know it's going to 0 already. If you're looking at something like just sum of n, well, I'm not worrying about that, right? We point out this as well. And this is a convergent, right? This one converges. And the next example, so that I can speak of that, oops, in green because I want to keep consistent here. Yeah, there we go, n squared, yeah? could naively look at this 1 over n to the negative 2, right? And that would be p is equal to negative 2. Yes? And you can say it's less than 1, right? Yeah? So I'm going to point out something here, right? And this means that it fails via the p-test. Yes? Everybody sees that? Negative 2 is less than 1, so it's going to fail via the p-test. Now, what's the problem with this one? We should not have gotten here. I mean, if we get to the p-test here, you blow past the nth term test, yeah, it will still fail. But you went to extra work. It was inefficient. That's not so good. And you want to avoid the inefficiencies as much as possible. Okay? There we are. So that's the p-test, guys, and that's a fairly straightforward one. Okay? And now I want to talk about our favorite test. Our favorite test. And this one is going to be, and this one right there is the one we're going to be using all the time when we get to the Taylor series. Because the Taylor series always work with powers of x and factorials. And for those, the ratio test just absolutely applies. Let me go ahead and give you an example on a ratio that we can work with, right? Okay, let me see if I got this open. Okay. Let me grab one that's actually from your homework. This one's good. Okay, so here's my example. Sum 16 to the n over n factorial. Okay? There we are. Now, let's look at this thing, okay? My first question, let's go through the flowchart. Let's go through the flowchart of this. Because you know this is about ratio test. We're going to use the ratio test. But let's go ahead and go through the flowchart here. First of all, does the nth term go to 0? Does the nth term go to 0, guys? Anybody? How can you tell? Okay. Well, there's a hierarchy. I've told you from slower to faster. It's one of the reasons why I do slower to faster rather than detail when they're talking about integration by parts. And the thing I like about slower to faster is, let's go ahead and remember what slower to faster looks like, right? Slower to faster looks like this. Let me get a cool color in here. Okay. That will still show up. Okay. Slower to faster, as in how fast they grow when you're working with them. Okay. And the answer is logs, then polys, then exponentials, and then factorials. Okay? Now, to be able to see that the factorial is faster than exponentials, it's enough to see that as you're expanding exponentials, you're always multiplying by the same number again and again and again and again, right? But with factorials, you're multiplying by a new number each time, but that new number gets bigger each time. When I'm at the 16th term on this one, The bottom is going to be canceling with the top. Okay, so let me give you an idea of what's looking at here, right? For n fact, for this right here, let's kind of like look at this just for a second. You're seeing 16 over 1 times 16 over 2 times 16 over 3. And these are like the first three terms. That's the third term, right? 16 to the first over 1 over 2 over 3 as I'm multiplying this up, for that's the 3 factorial, right? Now, eventually, by the time we get to the 16th term, you're looking at 16 over 16, right? And then, after that, everything after that is going to have something bigger than 16 following it, right? So this number here is going to be something that's fairly large but finite. And after I've blown up for a while on this, for the first 15 terms, it stops increasing when I get to the 16th term, okay? I'm talking about the term, the sequence that I'm adding, right? The nth term, the 16th term, stops getting bigger. And then every term after that starts getting smaller. And because I'm dividing by a factorial, it's going to eventually go to 0. So in this case right there, this I'm seeing something. The nth term is going to go to 0 because I have a power. I have an exponential, like a geometric, over factorial, and exponentials grow slower than factorials. Okay, so that implies, this implies the nth term is going to 0. So it passes, or I should say fails the divergence test, fails the nth term test, which is a test for divergence. Okay? We're all good. Kevin's here. Kevin's here. Okay, so Kevin showed up. I think I lost somebody else. I think Kayleen had it. Yeah, Kayleen's back. Okay. But I'm looking at right now at 10 people. That's good. Other than me, my clone. I'm seeing 10 students. And so who's the last person that was missing? I forgot again. It was Lourdes. That's right. I'm missing Lourdes. All right. And I think she wrote me or something like that. I don't remember exactly. Okay. So that's what that is. So there we are. Now, slower, faster, slower, faster. There we are. So let's go ahead and calculate the ratio here. Okay, so now I'm going to calculate the ratio. And for the ratio, what I'm going to look is the nth plus 1th term. Okay, I'm going to look at the n plus 1th term divided by the nth term. Okay. Okay, so we're going to calculate the ratio. A sub n plus 1 over a sub n. You can call it r if you like, doesn't matter. Okay, but I need to be able to figure it out. Okay, so let's look at what's the nth plus 1th term. Looks to me like 16 to the n plus 1, yes, over n plus 1 factorial. Okay, I know you'd rather have this with numbers, but you need this. You need to actually be able to do this with the n's in here. Okay, and what does the nth term look like? 16 to the n over n factorial. And this is going to be then This is the way you usually see it constructed as you're getting used to it. Let's turn that fraction over fraction, that compound fraction, into a simple fraction, just like this. And I'm going to stop here for just a second on that to make sure that you guys can see what I did. I'm going to blow it up a little bit because that's the important part, okay? You're going to see this happening all the time, and you need to be able to make this manipulation quickly and in your head, okay? What you're going to have is the first, this is the n plus 1th term, and this is the reciprocal of the nth term. And the reciprocal of the nth term just means flip tops and bottoms. Okay, and that's how we're going to do it. And once you're in this form, now nice things happen, right? What's 16 to the n plus 1 over 16? Anybody? 16 to the n plus 1 over 16? Over 16 to the n? Can people see that? I'm looking right here. Looking at this. Divided by this. 16 to the n plus 1 over 16 to the n. That's going to reduce just down to 16. Yes? Okay. Does anybody need that explained? Put your hand up if you do. Okay, let's do that, okay? And I'm kind of running out of space, but I can continue on left. Okay. Okay. So let me expand this slowly here, because I'm running out of room at the bottom of my screen. This is where I'm going, okay? This one is 16 to the n times 16, and this is 16 to the n. Okay? That's what we're looking at. That's what we're looking at. N plus 1 is 16 to the n times 16 to the first, and so this part just cancels. All right? And back over here, I could have seen this immediately, and this is the sort of thing you get used to. I could have killed this. Okay? Now, for the factorial part, this is the fun part, okay? Remember, n factorial is the product of n and the previous factorial. So n plus 1 factorial is the product of n plus 1 and its previous, which was n factorial. And that's the important part to see. That's the important part to see. Does that make sense, people here? I can toss a couple examples on the side if we need to. Okay, I'm actually going to do that just so that you guys can see it. Yeah. Do it as NB up here, kind of top of the screen. If I can make this thing work, behave for me. Okay. Yeah. Notice 6 factorial. Six factorial is 6 times 5 factorial. So 6 factorial over 5 factorial is 6 times 5 factorial over 5 factorial is 6. And that's what I just did. I looked at the n plus 1. Factorial factorial, and I divide it by the n factorial here, and end up with just n plus 1. Down here, I do the other way. I'm dividing n plus 1, n factorial by n plus 1 factorial. And I split up the n plus 1 factorial as n plus 1 times n factorial. And again, we can cancel these. And once I've done that, I'm looking at 16 over n plus 1. That's the ratio, guys. That's the ratio. Let's not lose track of the fact that this is just the ratio. Okay? Okay? And now my next question is, what's the limit of the ratio then? What's the limit of the ratio as n goes to infinity? And somebody should be able to answer this one. It does sometimes occur. No. As n goes to infinity? Okay. Say n was equal to 0. What would the ratio be? If n was 0, what's the ratio? 16. Yeah, it's going to go to 0. Yeah. As n's 1,000, it's like 16 over 1,000. Yeah. As n is 1,000,000, it's 16 over 1,000,000. So the limit is going to 0, and that's usually what you're going to see. That's usually what you're going to see. Generally on the ratio tests, you'll see the thing goes to 0. Yeah, you got a question?
Yeah. What if you, because like essentially you're just flipping the fractions to multiply them when you do the n plus 1. What if you flip the 16n plus 1 over n plus 1 factorial? You would get n plus 1 over 16, and then you'd be dividing by 0.
At that point right there, it would blow up. And if I was actually looking at that with the form that you're just talking about, it would not have passed the nth term test. Because you'd have the polynomial, the exponential, being overpowered by a factorial in the top. And
well, no, the factorial is gone at that point.
Say again?
The factorial would be gone at that point, I think. Oh, wait, no, I see what you mean. Okay. All right. So do you always flip?
You were talking about flipping these two. And if that was the case, then I was looking at factorial over exponential, and factorial wins. You know, train versus truck, you know? Truck is big, train is bigger.
So then do I always flip the 16n over n factorial to multiply?
You're generally wanting to see factorials in the bottom, okay? If you get factorials in the top, that's probably a bad sign. Because there's not a whole lot that's going to overpower a factorial enough to make it past the nth term test.
No,
and generally what you need is just a bigger factorial in the bottom.
I'm talking about, because you have the 16 over n plus 1 right here. The way I did it, I would have gotten n plus 1 over 16.
Well, that would be bad. That would be an algebra mistake somewhere in there. That would be an algebra mistake somewhere in there. Okay, because I mean there just isn't any way for that to happen. The n plus first term, right? The n plus first term on 16 to the n. Oops, I was trying to point, not right. The n plus first term here is going to be 16 to the n plus 1. That's going to be on the top.
Oh, okay. I see. All right, thank you.
Yeah. Yeah, and I know it takes a while to get this idea of like looking one further on. You're going one further on and hoping to find something smaller. So you're kind of like getting bigger on the ends, but getting smaller on the a sub ends. And keeping track of which one's getting bigger and which one's getting smaller is why we do homework problems. Okay.
Okay, thank you.
You bet. All right, there we go. Yeah. So anyway, that's how that and this is our favorite. This is the one we're going to use again and again as we're showing something called the radius of convergence for our power series that we'll be looking at starting next week. Okay? Now, yeah. This week again, what I'm mostly looking for this week is making sure that we get our incomplete exams back in so I can get those graded for you. All right, so we're ready to move on to the next test, the root test. Okay, and let me get my examples up on this one again. And frankly, this doesn't get used a lot. It just doesn't. Okay, but I'll toss an example in that we can see. And again, this one's going to be taken from your homework. I know I'm not zoomed properly right now. So here's the example. 6n plus log n to the nth power. This is the sum over 6n to the nth power. Okay? And as I'm looking at this example, I'm seeing nothing but nth powers, and that's what I'm looking for. Okay? So I'm seeing this just as I'm looking at it, I'm seeing this as 6n plus log n over 6n, everything taken to the nth power. And that was the one thing I had to abstract. I see everything, the whole thing. The original A sub n looked like a new series B sub n. 6n plus log n over 6n. It looked like that B sub n taken to the nth power, that thing inside. And when I see something, the whole thing taken to the nth power, and it's some complex expression, yeah. Because normally you want to think of that nth power right there, this looks like a polynomial or something like that. It looks like an exponential, right? And so you might want to look at the ratio test. And no, you don't want to look at the ratio test for this. This ratio test is not good for this one. But I see everything taken to the nth power, and so since everything is taken to the nth power, that's when I'm starting to think about, I can just get rid of the nth power and look what's inside. What's inside the nth power is the nth root. Okay? That's what we're talking about. If I'm looking at here, some series that looks like something taken to the nth power, another series taken to the nth power, or a series based on a sequence taken to the nth power, just pull out the root. Get rid of the nth power and take the root, and then look what's inside, and we're going to use what's inside with the root test. And this follows the same rules as the ratio test. If the root goes to, if the root has a limit that's less than 1, it will converge. And if the root is bigger than 1, it will diverge. And here's how you see that, okay? If the root is less than 1, okay? If the root is less than 1. We're looking at something like less than 1. Pick a number that's less than 1. 1/2 to the n? Yeah? And it looks like we're back at a p-test. Or, okay, so this is an exponential test. And at this point, I can go back to the ratio test. And that would be enough to see that this converges just the same way the ratio test does. Okay? That's going to be difficult to make out in the notes, so I'm going to pull that out. So we're just going to go ahead and continue with the root that we're looking at to check the test. Okay. So let's continue the example. I want the limit. I want to check out the limit of 6n plus log n over 6n as n goes to infinity. And I actually want to write that more cleanly. 6n plus log n over 6n. Okay? So look at this for a second and ask yourself what you're seeing. Okay? What do you think, guys? My first thing is I'm seeing like 1 plus log n over n. Just as a quick example as I'm looking at this. I lost my page. There we are. And I'm seeing this kind of looks like 1 to me. It really does. Yeah? This is the usual rule, say, right? L infinity, if they exist, of 6n over 6n plus L infinity of log n over 6n. Yeah? And this is 1. That should be immediate, but if somebody needs me to see that, I can do it, right? Yeah. On the other one, log n over n, y'all know that logs are slower than polynomials, right? And so this is eventually going to go to 0. And so the limit of my inside term is 1. Now, if the limit of my inside test is 1, then what do I have? What happens to the test if the ratio and root tests? If the rate, yes, it fails. That's exactly true. Osmalo, this one right here, it just didn't work. I can't do anything with this one. The test just fails. And more than that, this one's really bad. This one's really bad. Okay. This one right there, you would have to use other kind of more powerful numerical methods. I'm not going to give you all the possible methods that you could use. Okay. This particular example is an example of a series that you don't have a test. You don't have a test. And you're not going to have a test in this class as to what it is. All you know about this one right there is the root test doesn't conclude anything. Okay? So, let's try a different example. Make sure I'm in green. And move over here. There we go. Okay. Here's my new example. And for this example, I'm going to look at this. Sum n from equals 1 to infinity, which I won't always write, n cubed plus 6n to the nth power. Again, this is taken out of your homework. 7n cubed minus 2 to the n. Okay? And both the numerator and denominator are both taken to the nth power. Okay? And the idea is you just get rid of it. You just get rid of it. So I'm seeing this as n cubed plus 6n over 7n cubed minus 2, the whole thing to the nth power. So I throw away the nth power and just look at the root. All right. In general, you would look at the absolute value of the root, okay? But I wouldn't worry about that too much. That's not something that you really have to worry about. We'll just worry about L infinity. N cubed plus 6n over 7n cubed minus 2. Okay? And so my question is, what does this look like to you guys? We should be able to actually just you should be eyeball what the limit of this thing is. What do you think? Remember, anytime 1/7, that's exactly right. That's exactly right, Osmodel. Thank you. And again, anytime you're looking at these limits as it goes to infinity, your first thing when you're looking at polynomials is to get rid of all the minor terms. Anything that's lower degree term goes away. And so we think of this as n cubed over 7n cubed, and the limit then is 1/7, yes? So what can we say on this test? What can we say on this test? We say that, well, it converges. It converges. All right. I think I'm doing okay on time. Yeah. But I wanted to go ahead and because I've been using this all along, I wanted to make sure that we understood why. A lot of these right there, they fall back on the integral test. But it's not a test that you really want to use a lot. This is kind of like when all else fails, see if you can integrate it. Okay? Which kind of, defeats the purpose, right? So let me show you again real quickly why this works. Okay? So we have some series a sub n. Okay? And we assume whenever we get these things right there, it's past the nth term test. It's past the divergence test. Or should I say, failed the divergence test, so we know we have to keep on going, okay? So I've got something which is at least heading to 0. The nth term is heading to 0. So if I'm graphing a sub n versus n, I'm seeing something that I don't know. Is eventually going to 0, okay? So if I consider a sub n, if this thing lifts, because the series, the sequence itself that's underlying this is not a continuous function. It's defined for particular values of n. But if I replace the n with an x and get with and find myself with a continuous function, right? Then one of two things, I can add one of two ways. I can look at, this is the actual sum from 1 to infinity. So that's the actual sum, and it has to go through there, right? Now, the idea here is if I've got some function here, I can do one of the shifts, okay? I can look at either a continuous function that's running before as it comes through here. And at that point, you can see this particular integral. I don't know about this side, but everything, as soon as this thing becomes monotonic, and eventually has to become monotonically decreasing, okay, this part forward, the sum is less than the integral. Okay? Or I could have taken the other side and found from the right-hand side everything past here I reversed it, I'm sorry. Either the sum was greater than, or in this case, well, I changed my colors. Okay, I've got a sub n is going to be less than, if I look on the beginnings, a sub n is going to overpower the integral, or it's going to underpower the integral that I shifted by 1. In either case, because these are going to be off by a constant, I'll see that the one has to fall inside the other. And what that ends up giving me when I'm done is this kind of nice relationship right there, where the integral of f is less than the sum a sub n is less than the integral of f where I've shifted it. Okay? This is like 1 to infinity, 0 to infinity, 1 to infinity. Except that I turned that around again, sorry. And so what's happening on this is this forces going to force this thing to, if the integral of this converges, then so does this. And that forces this to converge as well. On the other hand, if this diverges, then so does this. And that is going to force this to diverge, because either the integral shifted is going to be less than the sum, or the integral shifted is going to be greater than the sum. And in either case, the shifted integral is going to either converge or diverge the same way as the unshifted integral. And so the integral itself, you don't have to worry about was it proving that it's less than or greater than, because that's like a really finicky part of the proof, and it runs it through there. Okay, now I believe I've got you guys till 10:30, right? Nominally? Yeah. Okay. And so that worked. I had a couple extra examples, but I don't see a whole lot of benefit in putting those through on this. Now, if there are any other questions, I will cover those. But other than that, I'm good. And so I'm going to stop the recording here and answer any questions you have.